carrying on this discussion on refraction, let's try to understand how refraction changes the path of ray of light. If we have a glass slab, naturally that glass slab would deviate the path of light. So if I draw a glass slab, a normal glass slab like this, if there was no glass slab over here, just assume that this is simply a hypothetical diagram, or rather an imaginary diagram. So my ray of light would come over here and go undeviated like this. But because there's a glass slab over here, what will happen is there would be refraction at these two surfaces. And eventually, as this is glass, and naturally glass has a higher mu compared to the mu outside, which in our case, for simplicity, let's take vacuum. So this would be 1, and I know that 1 into sine of theta, where sine theta is sine I simply, is equal to mu g into sine r, or mu g into sine theta of theta corresponding to the angle inside the glass slab. And as mu g is higher, sine theta inside the glass has to be lesser value, and when I increase theta, even sine theta increases. So naturally, over here, if my sine theta has to decrease, my theta has to decrease, which means if I draw a normal over here, my ray should come closer to the normal. This is the original path, and it has come closer to normal because mu g is greater than 1, which means glass is optically denser than the surrounding outside, or rather vacuum. Now, the moment it reaches over this surface, or rather interface, again there would be a refraction because outside there's a different mu. But now the situation has changed slightly. Why? For this new normal, this is denser medium, this is rarer medium. So rather than it's proceeding in this particular path, what will happen is it would shift away from the normal. And still again remember, 1 into sine theta, I'll just write theta 1 is equal to mu g into sine of theta g. Now the moment you're starting from here, this thing just shifts in the other way around. The reason I have not used an I and R thing over here is because in the first situation, this acts as your I and this acts as your R. But the moment the ray of light reaches over here, this thing acts like I and this thing acts like R, which means I will get a parallel ray, parallel to the original path, and there is a small shift in the path of light, and that shift is dictated by this thickness, which is highly intuitive. If you have a larger thickness of glass slab, naturally this would go to a higher position and would shift in a greater way. So this shift can be calculated using simple trigonometry, but we're not bothered with that because those questions would be of slightly different variation. This cannot be treated as a theory per se. So I can calculate delta, or rather shift in my ray of light, if I have been provided the thickness of the glass slab and the mu values, corresponding mu values. Now this forms the basis for a very interesting idea. That idea is apparent depth and apparent height. Let's understand what exactly is apparent depth and apparent height. If this is a beaker containing water, let the water height, or rather it has been filled till d units. So all throughout it's simply water. Now this can be thought of as vacuum. So I'll just write 1 refractive index of vacuum, and this is water. In place of writing mu of water, I'll just write mu. I can change this from water to kerosene, kerosene to glass, anything. This is anything but vacuum. Now, if there's a point over here, it could be a small coin, a dot, or a dust particle, or a letter written over here, an L or X or Y small letter. If I see it just vertically above this letter or point or dust or small particle, if I have to see my eye, this is my eye. I'm not drawing a diagram of eye because that would be highly complex and not needed in this particular situation. The eye has to receive the ray of light to process that image, and by that way you understand that there's an object over here. If you're looking vertically below, or rather just you're standing on top of that point particle, what will happen is a ray of light which travels in this direction normally would reach over here, and over here, as this is a case of normal incidence. When I say normal incidence, angle of incidence is equal to 0 degree, which means angle of refraction would also be 0 degree, because mu into sine theta is constant. The moment you put theta equal to 0, this thing over here goes away, which means even this thing would be go away, which means this refraction would be absent, rather no refraction taking place. So there would be no effect of a glass, water, kerosene, anything over here if you look at the image by just standing vertically on top of it. But that's not the usual situation, right? The way you look at images is it always at some angle away from the vertical. So eye would be somewhat over here or here, it could be here, anywhere around here. Now what will happen? A ray of light which travels in this path then refracts and then reaches your eye. That ray is essentially responsible for image formation. Let's try to understand that ray. Let's say this is the ray. It goes over here. But the moment it reaches this interface, this is my normal. If this is my normal, this is my angle of incidence. I can write this as I. But this is a denser medium and this is a rarer medium. So naturally, this won't be the path of light. This won't be the path of light. And it would shift slightly like this, away from the normal. Why from the normal? Because if I go from a denser to rarer, my mu decreases. So sine has to increase. And if I increase my sine, my theta also has to increase, away from normal. Now, if this is I, the original path must be I only. But the bigger angle, this has to be R. Now, my eye over here perceives every ray of light as they're not reflecting, refracting anything. They are just straight rays. I mean, there's a property called rectilinear propagation of light which says that light travels in a straight line. So my eye has kind of learned this idea that light can only travel in a straight line. What happens is the moment you see an object, rays of light come from that object and it reaches your eye. And your eye passes on those signals to your brain and image is processed according to that. So your eye has learned to pass on the signal to the brain that ray of light always travel in a straight line. So the moment it reaches over this point, my eye would retrace this path. But as this has been deviated at this juncture, it would reach over here only. Which means rather than seeing the object or the image of this object here, my eye would see the image here. Why? Because this ray comes over here, deflects like this, and my eye thinks that it is coming from straight below, not refracting. So this is the image which my eye would perceive, which means I have a shift. This is my shift in the object image situation configuration. So I have to find the shift in terms of depth. This is my real depth. I can write this D as real depth. And this thing over here, I can just simply write D prime or D prime or D dash, whatever you say. This is your apparent depth. And I have to calculate the value of apparent depth. How would I do that? I'll simply use simple trigonometry. How? This angle is R. I have just produced it backwards. So even this bigger angle over here has to be R. If this angle is R, this angle is 90 minus R, which means this is R. I'll read out this thing for you. This triangle, label it. This is your A and this is your B. So in this triangle ABI, this is your 90 minus R. Why? Because if I draw a normal over here, this would be R. So this is 90 minus R. So this becomes R. Or in other ways, these two lines are parallel. So these two angles would be same. And this is your T prime, D prime. Let this AB thing over here be some of X length. Now draw another triangle, ABO, the bigger triangle. If you draw the bigger triangle, what will happen is, see, these diagrams are not perfect to scale because it's a freehand diagram. So just consider that the same triangle has been constructed over here. Now, for this bigger triangle, this angle is I. So this angle over here is your I. If this is I, this is 90 minus I, this is I, and other way, these two are parallel lines. So this has to be I. And this thing is your D, real depth. Now, in this triangle, tan R would be equal to this perpendicular upon base, which is X upon D prime, and tan I in this triangle would be equal to X, same X thing upon D. If I divide these two things, I'll have relation between I and R and D prime, and that relation would be tan I upon tan R is equal to D prime upon D. Now, I know that if I and R are big, this formula would always be valid. But in situations when you're said that I'm just slightly away from the vertically above position, I'm slightly shifted away, which means this thing is an exaggeration. I'm not here, I'm actually over here. So all the angles would be very, very small. So very small angles, I can approximate tan as sine. See, just be careful over here. This is valid for all the situations, but in the simple case, when my eye is almost vertically above, almost, remember almost exactly above. If it's exactly above, there's no shift in image, right? Real depth, apparent depth are same. But if my eye is shifted slightly away from this vertically above position, the angles will be small. So I can approximate this thing as sine I upon sine r, which would be equal to E prime upon D. Not exactly sine I upon sine r. This follows from your first law of refraction that sine I upon sine r has to be the ratio of refractive indices. Now this is your first medium. This is your second medium. So obviously I'll divide 1 with mu. So this would give you 1 upon mu. What I do is I always divide the refractive index of the second medium with the first one. So first upon second. So rather second upon first. So this is second, this is first. Just rearrange this. What you would get is apparent depth d prime is equal to d upon mu, which is kind of intuitive because mu is greater than 1. So d by something greater than 1 would reduce d. So d would be reduced to d prime, which has been shown from the diagram also. Now there's slight modification over here. This question could be made, or rather this concept could be made slightly more complicated. If rather than giving you vacuum and a medium, I say this is of refractive index some mu 2 and this is of refractive index some mu 1, then what will happen? So don't worry, in place of 1 upon mu, what I will do is I'll simply write d dash upon d, which is sine I upon sine r, is equal to mu 1 upon mu 2, because this is my second medium. See, this may seem quite illogical to you, counterintuitive to you, but bear with me. This is your second medium, this is your first medium. So this upon this thing. Now if you do slight modification over this, what you would get is d prime is equal to d upon mu 2 by mu 1, and this gives you d upon mu of 2 with respect to 1. This thing is relative refractive index of the second medium with respect to 1. It's simple formula of relative refractive index, and this gives you the more general apparent depth formula. Mu of the second medium, rather the mu of the denser medium with respect to the rarer medium is the denominator, and this is the actual or real depth. Now this is a situation when I is looking at an object situated in water or a denser medium. But let's reverse the situation. Let's assume a situation in which the observer, or rather the eye, is not above the denser, away from the denser, but it is inside the denser. Then what will happen? See, over here you have to take one small liberty that this measurement is almost zero. It's negligible. I'm not here, I'm slightly above. So this measurement is almost zero. So that is an assumption which you have to take into account, because those things are very obvious, right? So in the reverse situation, your eye goes below and the object to be seen is above. Like you are swimming in a river or a pond or an ocean or a sea, and you have to see a bird or rather an aeroplane flying above you. So that situation reversed. So let's understand, what would you see? Let's say your eye is over here. This is your eye. And this is a thing which you have to observe. In this situation, you're vertically below the object. Take it as a straight line. I know it's not looking like a straight line, but just take it as a straight line. A ray of light following this path would go unrefracted, reach the eye like this. So I would think that the ray is coming from here. No change in your object image positions. So everything is fine. But that is not the case always. I'm slightly shifted away from this position, either in this direction, this direction. So again, the same logic applies. So you can pause the video right over here and think it through. What could happen now? What could be the apparent height? See, this is my real height. This thing over here is your real height. So what would be the apparent height? Pause it and just check what would be the answer. Now, again following the same logic, this is mu, this is 1, vacuum and denser medium. Let's say a ray comes like this. It reaches here, and this is your new normal. This is your I, angle of incidence. This is a denser medium, so naturally it would shift towards the normal. So the path which was like this won't be followed. It would shift like this. And this is your new position of I. So your eye would see that this ray is coming from behind, produce it backward. Naturally, this image would be at somewhat above than the actual object, which means I have a situation of apparent height greater than the real height. I'm not writing apparent and real heights because those are pretty obvious from the earlier situation. And how would I get it now? Now, this is I and this thing over here is R. I'll rewrite it for you. This is R. Now again draw A. This is B. If this is R, this angle is simply your I minus R. If you just take these two triangles, the bigger triangle over there, this is your AB, this is your I, and the smaller triangle. This is your O. This is your H prime. This is your H. Both are the same x. Now apply the same logic over here and I will leave it to you as an exercise. And naturally, if you do the same calculation, a similar calculation, what you would find out is H prime comes out to be H times mu, which means your apparent height has to be greater. That's why this formula comes, because mu has to be greater than 1. Now, in a modified situation, in a slightly complex situation, what will happen is I would give you that this is mu2 and this is mu1. So just think it through and what you will see that H prime becomes H times mu of 2 with respect to 1. These two are very similar situations. Only the case is that in first situation my eye is in a rarer medium, in the second my eye is in a denser medium. Rest all is same. Just the denominator becomes numerator, depth becomes height, rest all is same. Now this shifts my image, or rather it shifts the depth and height. And how much is the shift actually happening? Earlier it was at D and now it is at D by mu. So shift is D minus D by mu. Shift in this case, depth case, is equal to D minus D by, I'm taking the simpler case, I'm not taking relative refractive index formula because that would be needlessly complicating the situation. This would give you D 1 minus 1 by mu. And this is the formula for shift for every situation. As in the case over here which we have studied, a glass slab of D thickness. So if I insert a glass slab in the path of light and I'm looking at an object from the other side, so the position of object will be shifted, as in the image will be shifted by this much amount. How? Let's take a glass slab now again. If you look at from this position, if your eye is here, and this is your object, what will happen is ray of light will simply go unrefracted, no shift. But if the eye is slightly here or here or here, and the angle is small, mind you, if this distance is small compared to these distances, then I can use this formula. How? Let's try to understand that. At this surface, for small angles, it is going from a rarer to denser medium. This situation is coming, right? Which means if I think of refraction over here now, it would be coming like this, which means towards the normal. So if I produce it backward, it would be formed over here. This would be I dash. Now, in this situation, it was going from this side to this side. In this situation, in the other way around. So this can be thought of as the case of apparent height. This was your real height and this is your apparent height. If I label this thing as A and this as B, my AO is original height or real height and AI prime is apparent height. This would be equal to 1 by mu of this glass slab. So what is AI prime? This is simply AO times mu. Now, this forms the basis for refraction at this surface now. Now from a denser to rarer medium. So now what will happen is, it will go away from the normal. So I'll produce it backwards. So now I'll have to use the depth formula, which means this thing over here, this becomes my actual depth, AO times mu from A. I'll have to use this also because it's taken from this B point. If D is the thickness of the glass slab, so plus D. So AO times mu plus D gives you the actual depth. This upon mu would give the apparent depth, right? And this would be equal to AO times D by mu. So actually this has to be D plus AO. Real depth or real location should be AO plus D. But what I'm getting, this apparent thing is AO plus D by mu. So shift would be equal to my real minus apparent. If you just subtract these two things, what you would get is D 1 minus 1 by mu. So the same formula comes over here. Unknowingly, we have done a remarkable thing. No matter where we keep this glass slab between the eye and the object, my shift would be the same quantity. D, the thickness of the glass slab or whatever the medium it is, it could be anything, into 1 minus inverse of refractive index of the glass slab. And in the complicated situation, if this is of refractant index, let's say mu1, this is mu2, then the formula would change slightly only, and this would become d 1 minus 1 by mu of 2 with respect to 1. This is just a needless complication. This doesn't add much to the concept of real and apparent depth.